Hello, everybody. Welcome to the afternoon session. I hope you have a nice lunch. And now we continue with the tutorial session about astrophysical plasmas. Our presenter is Chris Hamilton from the Institute for Advanced Study. And the title of the talk is Kinetic Theory of Stellar Systems, or Dynamics in Translation, How Mathematics of Plasma Describes the Physics of Galaxy. So you have the microphone, very welcome, and let's go.
All right, thank you very much for the introduction, and thank you everybody for being here. We've made it halfway through the conference, and you should think of this as a kind of halftime at the Super Bowl. A bit of light entertainment before everyone gets back to the serious business of plasma physics. I'm here because I'm not a plasma physicist. In fact, I'm not. Despite the title of this session, I'm not a plasma astrophysicist, and this is not really about astrophysical plasmas. You'll see what it's about in a moment. So the real reason I'm here is that I'm currently writing a tutorial article for the journal Physics of Plasmas called Kinetic Theory of Stellar Systems, or Dynamics in Translation, something I'm writing with a collaborator of mine, Jean-Baptiste Fauvry. And the idea is to show plasma physicists, as well as astrophysicists, how one can take plasma mathematical ideas and use them to solve astrophysical problems, or perhaps even vice versa. So I'm not a plasma astrophysicist. Some of my best friends are plasma astrophysicists, nothing wrong with that. Instead, I'm a stellar dynamicist, or what you might call a galactic dynamicist. So I'm not going to be talking about cosmic ray propagation through the IGM or magnetic fields or something like that. In stellar dynamics or galactic dynamics, in case you don't know, we're basically interested in how do systems like this evolve over timescales of billions of years. So how do the spiral arms arise in this galaxy? How do the stars get from the outskirts towards the center? These are the kinds of questions that we're interested in. And we have amazing data these days. And I would say actually that the data is way ahead of the theory. And that's where plasma physics tends to come in. So I can't teach you galactic dynamics in an hour, right? Despite this being a tutorial talk, I'm obviously not going to be able to do that. So instead, I'm going to take a bunch of case studies. And the first thing I want to do is to basically tell you that stellar dynamics is plasma physics. But we're actually about half a century behind you lot. What do I mean by this? So if I start with this paper from 1972 by Robert Dewar, Dewar was looking at the amplification, the Landau growth of some electrostatic wave. That's the green thing you see there. And Landau tells us that that wave will grow exponentially with some Landau growth rate. But of course, exponential growth can never last forever, and so the wave must at some point saturate. And Dewar realized that this would saturate because particles would start to get trapped inside the trough of the wave. And he derived this saturation condition, which said that the wave would saturate when it got so strong that the bounce frequency, this omega b thing here, of particles at the trough of the wave was equal to 256 over 9 pi squared times gamma, with gamma being that linear Landau growth rate, okay? 50 years later, I posted this earlier this year to the archive, which is on the saturation of spiral instabilities in disk galaxies. So you see this beautiful spiral galaxy here, this is M51. You see it has these two very large grand design spiral arms. In fact, one of the leading theories for what these spiral arms are is that they're just the galactic analog of one of these unstable waves that you have in plasmas. Okay, they're unstable linear waves of the underlying distribution function. But they, of course, don't exponentiate forever. We see spirals that have some finite amplitude. And it turned out that nobody had really looked into it quantitatively of why do spirals have the amplitude that they do. And the reason that they stop growing exponentially is that they start to trap stars. You're not trapping electrons now, you're trapping stars inside the gravitational potential of the spiral arms. And if you do that and you find that the stars start to librate around the bottom of the potential, they have a bounce frequency, which is 256 over 9 pi squared, square root of m times gamma. Gamma is, again, this growth rate. And m here is the number of spiral arms. So in this example here, m would be equal to 2. But for a one-armed spiral, the problem of saturation of a spiral and saturation of an electrostatic wave are completely isomorphic to each other. So this is the sense in which I mean that galactic dynamics really is plasma physics, but it's plasma physics of 50 years ago. Okay, so the outline for the talk is that I'm first going to introduce you to what stellar systems are. I'm going to assume you know absolutely nothing about astrophysics. I know that there are people in this room who know much more astrophysics than I do. I don't mean to offend anybody, but I'm going to assume you know nothing. And then I'm going to take a couple of case studies first of all, talk about structure formation on very large scales, and then talk about the dynamical friction on galactic bars. Don't worry if you don't know what these words mean, you will by the end of the talk, and show you how in all of these cases, plasma theoretic techniques are what we need in order to describe the universe. So let me start with an introduction to stellar systems. There are kind of two mental models that I want you to have in mind. If we start with the one on the right, this is what we call a globular cluster, okay? It's kind of like a swarming beehive of stars. It has something like 10 to the 5 stars in it, and they're all moving around in random directions, pretty much, swarming around. And so we call this a hot system because any given star doesn't have any particular preferred direction of its velocity. It could be going in any random direction. These things are dotted all over our galaxy, but each of them is about 10 billion years old, which is comparable to the age of the galaxy. And what we're going to find actually is that the dynamics of these systems is in some ways, not always, but in some ways quite boring. It's actually quite a lot like a plasma on scales much, much smaller than a Debye length, where you just need to worry about one electron or ion flying past another and giving it a little nudge. That's basically the physics of how a globular cluster evolves. A much, much more interesting system is the one on the left. This is a much larger system. This is a galaxy, a disk galaxy. We're looking at it face on here, but if we were to look at it from the side, it would be very, very thin, like 2 fried eggs glued back to back. It's a much larger system. It's also what we call dynamically cold. That is to say that the stars in this case are not going around in random directions. They're all moving around on pretty much circular orbits, and they're all moving in pretty much the same direction. So this is a cold, rotating disk. The age of this system is about the same as the age of the globular cluster. But the orbital period in this system is much, much, much slower, simply because the system is enormous. Okay, so those are the two kinds of systems. The one on the left is much more dynamically interesting. That's going to be analogous to a plasma on scales larger than the Debye length, where you can have interesting collective fluctuations. You see that the spiral arms and so on that you have here, these are actually collective, possibly instabilities and dressed interactions that you have in plasma physics on large scales. So the basic thesis of this talk is that stellar systems are nothing more than collisionless gravitostatic plasmas. Let me take the second word of that first, gravitostatic. Well, that's the obvious part, right? In a plasma, an electrostatic plasma, the force between any two particles is just Q1 times Q2 divided by the distance squared, where Q is one of each of the charges. Similarly, a galaxy is, to an extremely good approximation, simply described by Newtonian gravity. And so the force between any two stars or any two masses of any kind is just M1, M2 divided by R squared, of course, with a crucial minus sign. So that's the gravitostatic part. And these are also pretty much, to a reasonable approximation in most cases, collisionless systems, which means I can describe them in exactly the way I would describe a collisionless plasma using a Vlasov, or what we like to call in galactic dynamics, collisionless Boltzmann equation, dF by dt equals 0. Now, how do I get to that point? I've just pulled that out of the air. But where do you start with your kinetic theory of plasmas? You start with Spitzer. Okay, one ion or one electron flying past another. That's also exactly where you start in the kinetic theory of stellar systems. This is lecture 1 in kinetic theory of stellar systems. So I told you that these systems are roughly collisionless. What do I mean by that? Well, in a plasma, you mean that you don't need to worry about individual two-body collisions. And I'm going to now show you how you do exactly the same calculation in a galaxy. So suppose that I just ignore the fact that the galaxy actually looks like this, some horrendously complicated rotating thing with an awful geometry. And I just take a single test star and pretend it's moving in a straight line along this unperturbed dotted trajectory here until it interacts with some field star. The field star is the red one and it has a mass m. And the interaction happens at some impact parameter b and the test star just flies straight through. Well, what happens? Of course, the test star feels a little nudge. It feels a little nudge, which is delta v. And if you work through a little bit of algebra and do an integral, you find that this delta v, the size of the velocity kick that the test star feels, is 2gm, where m is the mass of the field star, divided by bv. Now, exactly the same calculation as what Spitzer did. You now say, in a time capital T, how many of those interactions do I have? Well, let me just pretend that the field stars are distributed randomly and homogeneously everywhere in space. And how many of them do I encounter? And then I'm going to get a random walk in my velocity because of those encounters, and I sum those up and I get this formula on the bottom right-hand side. This is the total mean square kick to my velocity that I get in a time t. very, very similar to plasma physics. Of course, we have a Coulomb logarithm here. I won't go into the details. You know them better than I do. We now define the Chandrasekhar, or rather the Spitzer, two-body relaxation time of the system by saying, how long does it take until those little delta V squareds add up until they're equal to my initial velocity? Or equivalently, how long does it take for the star to forget its initial conditions? How long does it take a star that's on some orbit to undergo so many two-body encounters that its orbit is changed completely? And the answer is what we call the two-body relaxation time. And that's roughly n, which is the number of stars in the system, times T dyne. T dyne is the dynamical time. It's the crossing time, the orbital period. Okay, so that's a lot of formalism. What does this actually mean? So the two-body relaxation time is n times the dynamical time. Now, if I go back to here and look at my globular cluster, well, all I need to do to work out this two-body relaxation time is multiply those two numbers at the bottom. The globular cluster has something like 10 to the 5 stars, and it has an orbital period of about 0.1 million years. If I multiply those two things together, I get 10 gigayears. So roughly in a globular cluster, on the age of the cluster, with 13 gigayears, remember, is the age of the universe. On the age of the cluster, these two-body relaxation process is pretty important. If I look at the much more interesting case of the disk galaxy on the left, the number of stars there is 10 to the 11, okay? 100 billion. And now I multiply that by the dynamical period, which in this case is about 100 million years. For the sun, it's even longer. It's about 200 million years, the time it takes to go all the way around the galaxy once. If I multiply those two things together, I get a naive Spitzer or Chandrasekhar relaxation time, which is 10 to the 10 gigayears. This is 1 billion times longer than the age of the universe. And yet, we know that galaxies like this, including our own, do evolve very dramatically on timescales of 1 billion years, 2 billion years, and so on. We know that by looking at stars and tagging them chemically and looking at the distribution function of stars in the solar neighborhood, and for all sorts of other different reasons, we know that these galactic systems do evolve on much shorter timescales than this. And so two-body relaxation is clearly not the only process in town. And so that's where the plasma physics is going to come in. Okay. Why is it that these gravitational systems are able to do interesting things on very large scales? If you look here, I clearly have coherent in the left figure. I clearly have coherent motions, these kind of spiral wispy arms, over scales that are comparable to the scale of the entire galaxy. How is it that stars at one part of the galaxy and stars at the other part of the galaxy are able to talk to each other? Well, the basic reason for that is that gravitational polarization is a kind of anti-Debye shielding. Okay? Let me say what I mean by those words. Here's a plasma. It's a pair plasma. It has blue positive stuff and red negative stuff. And so it's quasi-neutral overall, but now I put in a couple of probes. I put in a red negative probe and a blue positive probe, and you all know what happens. I form little Debye spheres. So around each of these probes, I form a Debye sphere which is surrounded by the particles of the opposite charge. And so that shields things on large scales, on scales larger than these little green circles here. And that's what we call a Debye length. Okay, I don't need to tell plasma physics audience this. But know that in a plasma, pretty much always, the Debye length is always much, much smaller than the system size. Even though you have tons of particles within the Debye length itself is small compared to the size of the system. On the other hand, this is not going to be true for gravity. So suppose instead I do exactly the same thing, except now I take a box of stars and I introduce into it a heavy perturber, some point mass. That's just the black dot here, which is moving through this box of stars with some velocity. What happens? Well, unlike in a plasma, it actually gathers an overdensity around it, and the underdensity is far away. So this blue stuff here is an overdensity, meaning that in a gravitational system, the collective interaction, the polarization, the Debye shielding, if you like, actually increases the effective mass of the perturber, whereas in a plasma, it would have decreased the effective charge. Okay, Debye shielding decreases your effective charge. Gravitational polarization increases your effective mass. Not only that, but remember that the Debye scale was much smaller than the plasma itself. But in this case, this is effectively the Jeans length, if you know what that is. Don't worry if you don't. This overdensity, this blue region, is effectively on the scale of the entire system. So this is simply the fact that gravitational interactions are not screened. There is no two signs of the mass. There's only ever attractive interactions. And stars on one side of the galaxy are always talking to stars on the other side of the galaxy, and you can't get around that. And that leads to collective amplification of oscillations on very, very large scales. A slightly less, this was a box of stars, a kind of silly idea, which doesn't really exist in nature. Here's a different example of something similar. This is a heavy perturber inside a disk galaxy. So this is an n-body simulation of a disk galaxy. You see that at time 0, I've just put a perturber in on some circular orbit. And about one orbit later, 250 million years, that's about how long it takes the sun to go around the galaxy, you see that there's this large overdensity over here. And that this overdensity actually has a characteristic scale, which is damn near the sort of scale length of the entire system. It's not confined to some small region around the perturber. You get some large scale amplification. Gravity likes large scales. Okay. So that's a heuristic picture of how this works. Now let's talk a little bit about structure formation and say how some of the things about linear theory that you know of in plasmas can tell us the scales on which galaxies form. So we think that the universe is threaded with this stuff called dark matter. All of structure formation comes out of dark matter, meaning that originally the universe was supposedly filled with very, very tiny fluctuations of this dark matter, and those fluctuations clumped together and formed something like this. This is, of course, is a simulation, not an observation. But the black tendrils here are the dark matter overdensities. And the little bright spots are places where gas, baryons, the stuff that you and I have made of, have fallen into the gravitational potential of those dark matter nodules and formed galaxies. And so they shine. Okay? But why are the characteristic scales in this picture what they are? Why not 10 times larger, 10 times smaller? So to answer that, suppose I was to zoom in on this little blob here, I might see something like this. So this is another simulation, a cosmological simulation. And in the first box here, this is what the dark matter overdensity looks like at some position. So the light colors here are tracing the dark matter. And you see that as time goes on, the dark matter starts off in this gassy kind of diffuse picture, and eventually it forms these clumps and filaments and forms these little overdense regions. Now, why does this happen? Well, the physics of this is extremely simple. Suppose that I just have a load of dark matter particles that are all moving around with some random velocity sigma, and I clump a few of them together, and I clump them together on some length scale L. Well, if they weren't moving at all, if it was just a completely cold system, then you can easily show that the time it would take that whole green blob to collapse in on itself is roughly 1 over the square root of g rho, where rho is the density of the ambient medium, okay, the basic density of the dark matter. On the other hand, if there was no gravitational interaction, but the stars were moving, dark matter particles, not stars, sorry, the dark matter particles were moving, they would be able to escape the green circle on a timescale roughly of L divided by sigma. Sigma, again, is their typical velocity. So if the escape happens on a timescale long compared to the collapse, then I expect collapse. And so heuristically, I can say that any gravitational system like this will be unstable on scales larger than L, bigger than something like the square root of g rho divided by sigma. That's the basic physics of Jean's instability. And that gives you a length scale, which is something like 100 kiloparsecs, which is exactly the scale on which cold dark matter halos tend to form, galaxies tend to form inside them. So that's a heuristic idea of how this works. If I was to try to make this mathematical, I get to plasma physics. So how do if I have some instability, clearly this is effectively a nonlinear phenomenon eventually, but any good nonlinear instability has a little linear phase to begin with, and we can understand it. So the way to do this is to use linear response theory. Like I told you, the galaxy, the dark matter distribution function here, because it's a collisionless system, just satisfies the Vlasov equation, df by dt equals 0. And it also satisfies the Poisson equation, which is nabla squared of phi here being the gravitational potential, is equal to 4 pi g integral of velocity over f. So f is sourcing its own gravitational field, and all I need to do is solve these two equations self-consistently, like you've done in plasma physics since you were in short trousers. The way I do it, of course, is that I take f and phi to be equal to some large-scale, homogeneous, dominating part, plus some small fluctuations. I do the thing that we did many, many times as undergraduates, and I get out a linear theory, and I find that this linear theory has modes, has large-scale coherent oscillations, which are zeros of this dielectric function. Of course, there's no electric field here. It's not really a dielectric. And this epsilon k is 1 plus 4 pi g over k squared times this integral that we all know and love from Landau. Now, if I take f naught to be a Maxwellian, for instance, I find that this gravitational system is unstable for wavelengths k less than the thing that you see there, which is essentially 1 over the L that I showed you before. So this is the critical wave number, below which you will have instability, above which you'll have stability. Now, you might ask, okay, but this is all plasma physics, but if I use a Maxwellian distribution in plasma theory, I don't get instabilities. Well, physically, that's because in plasmas, you don't have everything being attractive. You have quasi-neutrality, and you have, if there's a region of positive charge, then negative charges try to rush in. Mathematically, all this comes down to is the fact that there's a difference in sign here, where epsilon is 1 plus something in a gravitational system, epsilon is 1 minus something in a plasma system. And so a Maxwellian that would never give you an instability in a plasma does exactly that for galaxies. Okay. All right. So the stellar systems that I've told you about so far have been rather fictitious in that they've been kind of boxes filled with stars. You can't have a box filled with stars. You don't see any box-shaped galaxies. And so, in fact, I should be telling you about inhomogeneous systems and orbits and so on, and that's what I'm going to do now. And I'm going to do it through the guise of a paper that we wrote. By we, I'll show you who I mean in a second. You might recognize some of them, on dynamical friction on galactic bars, or to put it in the language that's more appropriate for this conference, nonlinear wave-particle interactions with diffusion. So this is a paper that I wrote with Elizabeth Tolman, Lev Arzamasky, and Vinicius Duarte. Probably at least some of you know at least some of them. All of these people are plasma physicists. None of them had done galactic dynamics before this project. In fact, Vinicius there on the end had never done astrophysics before this project. But it turned out that their expertise in plasma theory was exactly what we needed in order to solve this astrophysical problem. So let me show you how that worked. Also, if you're interested in these kind of things, Jeff Less has a talk later on this afternoon on a related idea. And Nick Pham had a poster, which I think is down now, but you can still look at on the online version. Okay. So we think that structure forms with this dark matter stuff. And again, I'm going to zoom in on one little patch. If I zoom in on that one little patch, what might I see? Well, here's a $10 billion photograph. This was one of the first images from the James Webb Space Telescope. This is a galaxy cluster. And a bunch of the galaxies in here will be gravitationally bound. This is just to give you an idea of the scale that we're talking about. Now, if I zoom in on this little blur here and blow it up, it looks something like that. Okay, that's not very impressive, but suppose that I had James Webb to the power of 10, it might look something like this. Okay, this is M51. This is a whirlpool galaxy, a spiral galaxy, pretty near the Milky Way. It has these amazing spiral arms. In this case, it actually has a companion galaxy, and that's what's driving the spiral in this case. Now, that's all very beautiful, but this galaxy is actually kind of weird. And the reason it's weird is that it doesn't have a bar. Now, you might not know what I mean by that, but you will when I show you the next slide. This galaxy has a bar. Okay. This galactic bar is this big elongated collection of stars, quasi-rectangular thing at the center of the galaxy. And as you might guess, it's rotating. That's not a simulation. That's just So it's rotating. And so we typically think of this galactic bar as being some kind of rectangle or elongated thing, which is just spinning at the center of a galaxy. These are absolutely all over the place. Most galaxies have them. Depending on who you ask, it's between sort of 60 and 80% of galaxies actually have these bars. And these bars have caused a lot of controversy in recent years, partly because the bars that we observe in the universe seem to be spinning too quickly. That is to say, when we look out into the universe, we try to measure the speeds at which these bars are spinning at the centers of galaxies. The answer that we get is too large compared to theory. And theory here really means simulations of the standard model of cosmology. It really means lambda CDM, so cold dark matter simulations like the ones that I was showing you before. They tend to form bars that have slowed down. So they're not spinning very rapidly. I mean, this has led some people in the last few years to say that dark matter is useless. We should just get rid of it, abandon it, go for something else entirely. I would say that's a little bit premature. But for the purposes of this, I just want to understand why it is that a bar might slow down. So like I showed you before, each one of these galaxies is surrounded by a dark matter halo. Okay, it's surrounded by dark matter. And in fact, the dark matter is thought to be the thing that dominates the gravitational potential of the galaxy. Not the stars, not the gas. The dark matter is the dominant thing. and it's a sort of quasi-spherical thing. So if I replace this entire galaxy, all this complicated mess, with just this cartoon picture here at the top, what will happen? So the yellow thing that you see there is the bar. It's rotating anti-clockwise, according to the white arrows. And it's surrounded by this gray sphere, which is supposed to represent the dark matter. Okay, so now I'm going to try to spin a bar made of stars through this medium of dark matter. This is a simulation from Cheever and Schoenrich. You see that the dark matter basically sloshes around in response because the dark matter is gravitationally coupled to the bar. So it's just like trying to twiddle your spoon at the center of a cup of coffee. The coffee starts to move around. But you'll see it's not quite like coffee. It's more like molasses. Why is that? Well, so suppose I've frozen the simulation here at about 0.5 gigayears. And the dark region at the top left and the dark region at the bottom right represents an overdensity of this dark matter stuff. So I started off at time 0 with a completely spherically symmetric, nice quiescent dark matter distribution. And now I have something that has an overdensity on the top left and an overdensity on the top right. What's this going to do? Well, if I go back to this cartoon picture, remember that I saw that I had a box of stars and I tried to plow something through it. And I formed this large overdensity, this blue overdensity. But if you look at it a little bit more closely, you see that the blue overdensity is not centered on the point mass. It's centered somewhere behind the point mass. So the blue overdensity is awake that the point mass is gathered behind it and is now going to try to drag it back. So this is dynamical friction. This is Chandrasekhar's picture of dynamical friction. It feels the point mass, the perturber, feels this drag force. In other words, if I now just translate this into a rotational system, the bar is going to feel a drag force because it's trying to rotate anti-clockwise, but it has an overdensity which is opposing it and trying to pull it back. And so the bar is going to try to spin, but the dark matter particles are going to try to pull it back. And so the spin is going to slow down. The rate at which the bar is spinning is going to decrease. So this is dynamical friction. So clearly, if you want to argue about how the observations compare to the theory, you need to understand this process. Okay, the observations of how fast are bars spinning compared to how fast they should be spinning. So in order to talk you through how that actually works in practice, I need to tell you something about orbits. So first I'm going to talk to you about what I've even stripped away the bar now, right? So I just have a purely spherical potential, and that's just created by this dark matter halo. And so every dark matter particle inside this dark matter halo is just orbiting in this spherical potential. And what happens? Well, all of the orbits look basically something like this. Okay, they look like rosettes. What that means is that you can think of each of these orbits, the black line is some dark matter particles orbit. It consists of two oscillations. First of all, it's going round and round azimuthally, but it's also going in and out radially. So you can think of this as a superposition of two orbits, one of which is azimuthal, one of which is radial, between the green radius that we call the pericenter and the blue radius that we call the apocenter. And it just goes on and on and on like this forever. Here are a few other examples of dark matter orbits in this potential. Note that they look different from each other, but they all have the same structure. They all look like these rosettes. They have this constant pericenter inside and this constant apocenter outside. And the only difference between them is the ratio of the pericenter to the apocenter, basically. But they all look like these rosettes. They can all be described very easily mathematically. Now, this is the point where in an astrophysics talk, everybody groans because they hate angle action variables, but this is a plasma physics audience. So of course, you all know what angle action variables are already. So in case you don't, actions are just what you would call adiabatic invariance. The fact that you have a superposition of oscillations, one going in and out and one going round and round, means that you have adiabatic invariance. And so rather than doing the kinetic theory in terms of positions and velocities, x and v, it's better instead to do it in terms of angles and actions, theta and j. And j's are these adiabatic invariants. I'll show you what they actually are in a second. The nice thing about angle action variables is it means that the angles, theta, they just evolve linearly in time, and the rate at which they evolve is some function of j, whereas the j's themselves, because they're adiabatic invariants, they're just constant. So we always describe galaxies in terms of angle action variables. Another way to say this, okay, so for central potentials, so for the spherical potential that I was dealing with here, for these kind of rosette orbits, there are two adiabatic invariants that you need to worry about. One is just the angular momentum. It's what is the angular momentum going around the phi axis here. And the other one is very similar to the adiabatic invariant that you get inside a magnetic bottle. Oh, it's crossed off. So this should be JR. It's hidden underneath this box here. So JR, this JR here is this formula here, which is extremely similar to the adiabatic invariant you get when bounce averaging something. In other words, the action just tells you which orbit you're on. What does your rosette look like? The angle tells you where you currently are within that orbit. And there's also this capital omega, which is a frequency, which tells you how rapidly do you go around that orbit? How rapidly do you go in and out? How rapidly do you go round and round? That's all there is to it. And so if I go back to these same three examples, there are things with low radial action where the radial part is not very important compared to the azimuthal part. They look almost like circles. On the other hand, the ones where the radial motion is more important than the azimuthal motion, they look like these very elongated donut things here. And the middle case would be where the two actions are comparable to each other. But I can always describe any set of orbits using these actions, and the dark matter halo itself, or a galaxy itself, is nothing more than a collection of orbits. So if we understand the orbital structure of a galaxy or of a dark matter halo, then we can say that we understand the system. In fact, much like the electron velocity distribution now, measuring this and understanding its properties in the solar wind is a whole industry. As of about 5 years ago, the same is now true in the galaxy. So this is an artist rendering of the Milky Way galaxy, and the sun here would be the little green star. And we've sent up this spacecraft called Gaia. The data is now actually better than this. This was several years ago. If you look at this little patch around the sun, this is what we call the solar neighborhood, and Gaia has managed to measure the positions and velocities of about 2 billion stars within that patch. And in fact, it's not only able to measure that, but given some very weak assumptions on what the potential is, you're able to measure these integrals of motion, these adiabatic invariants, the angular momentum and the radial action. So this is what the distribution function of stars looks like in the solar vicinity. So understanding this distribution is now a major industry. That's what a lot of galactic astronomers are interested in trying to do. Okay, that was stars, but back to dark matter. So you know that I can describe the unperturbed dark matter halo as a collection of orbits. That's all very easy. So now I'm going to say, how does those orbits interact? How do those orbits get shuffled around when I introduce the bar? So any individual dark matter particle, it has a Hamiltonian H, which is equal to some kinetic energy, v squared over 2, just how fast is it moving, plus phi 0. Phi 0 is this underlying spherical background potential that's just created by the spherical distribution of dark matter, plus a little perturbation, delta phi. And this delta phi is the gravitational potential of the bar. So you can think of this as just a wave-particle interaction. In fact, the bar potential has this form here. It's slightly complicated, but the only important thing is that it has this cosine of 2 phi minus omega pt dependence. That is to say that the bar is just rotating at some rate, capital omega p, steadily at the center of the galaxy. And the question is, how do the dark matter particles respond to this rotating bar? Another thing to say is that typically, well, this depends exactly where you are in the galaxy, but typically the strength of the bar potential compared to the overall energy of the background is something like 2%. So you might think this is a weak perturbation, and I can do perturbation theory. The advantage of going to those angle action variables is that now mathematically, this becomes very, very simple. So the underlying Hamiltonian that just describes the motion if there was no bar only depends on the actions. And the part that depends on the bar depends on angles and actions and time because the bar is rotating. But this is just a wave-particle interaction in some nice coordinates. So what we actually want to compute is the friction that the bar feels, that frictional force, that dynamical friction. And it's going to be a torque, right? The bar is losing angular momentum because it's trying to spin its way through this dark matter, and the dark matter is trying to drag it back. How do I calculate that? First of all, I just write down the torque on a single halo particle, a single particle of dark matter, that's dLz by dt, and it's equal through Hamilton's equations to this formula minus d delta phi by d theta phi. If you don't know where that comes from, don't worry about it. The point is that you can write this down analytically. We know what the bar potential is, so we can just write this formula down exactly. Now to get the total torque on the bar, I just use Newton's second law, and I say that the total torque on the bar must be equal to minus the total torque on the halo. So the total torque on the halo is just, I take this formula here, I multiply it by the number of halo particles, the distribution function at any given phase space location, theta and j at time t, and I integrate over the entirety of phase space. And that gives me the total torque that the bar feels. Now, the challenge, of course, is that I don't know what F is. Because F is this awful complicated thing, because the dark matter particles are sloshing around all over the place. I showed you the simulation where it looks like a complete mess. How do I actually compute it? Well, we know that it solves the Vlasov equation, but as the people in this room know all too well, that doesn't get you so far. It's pretty difficult to solve that thing sometimes. So the first attempt to try to solve this problem was by Lynden-Bell and Kalnice in 1972. For the experts in the room, yes, they were talking about spirals, not bars, but keep your mouth shut. So Lynden-Bell and Kalnice said, how can I compute the solution to this Vlasov equation? Well, I'm just going to use linear theory. The bar is a 2% perturbation, and so I'm going to treat it as a linear perturbation, and I'm going to do linear theory. Here is the bar potential, delta phi. The change in the distribution function that I get as a function of time is just found by integrating over delta phi, and it depends on the background distribution function, or rather the gradient of the background distribution function. Just like in a plasma, you'd have df naught by dv here. The ends here are more or less what you would call k, wave number, wave vector rather, except in this case, they're integer multiples. So the people who do tokamaks know about this. These are just 1, 2, 7, -1, 3, 4, whatever, something like that. 3 numbers, 3 integers. But you think of them just as k's. So there's a formula. All I need to do now is take it, plug it back into here, solve. If you do that, what you get is what we call, and you wait for a long time for some transients to die out, what you get is what we call the time asymptotic Lynden-Bell-Kalnice, LBK, torque. And it looks like this. It has this delta phi squared in it, so it depends on the strength of the bar potential squared. It has this gradient inside, and it's also a resonant effect. Resonant because we have this delta function here. Remember, omega is the frequency of an individual dark matter particle, and omega p is the rate at which the bar rotates. So Lynden-Bell and Kalnice are telling us that the only torque that you get after waiting a long time is by looking over all the possible particles with all the possible j's and finding the ones that resonate with the bar. Okay? It turns out that this gives you a finite number. For most sensible distribution functions, that number is negative, which is what we expect, because that means the bar will slow down. Torque negative means friction. And it's resonant in the sense that I've just said. But you should be screaming one thing at me at this point, which is that this is just Landau damping. Okay, this is essentially the Landau damping formula written in angle action variables. Sorry. All right. But there's a problem with it. It doesn't work. The reason it doesn't work is that if you take this formula and now you say, okay, now I know how the bar is going to evolve. I've worked out the torque on it. It's going to slow down in time. Let me just predict it. What you'll find is that the pattern speed of the bar starts at some large number and very rapidly decreases to some small number. That's a theoretical prediction based on this formula. But like I just said, the bars in the real universe are moving quickly. They're not spinning slowly, they're spinning quickly. And so something seems to have gone wrong. What's gone wrong? Well, what's gone wrong is exactly the same thing that goes wrong with Landau damping. So here is a simulation. Now we're in phase space. So we're in the space of angles and actions. But if you like to think of it in plasmas, this is just position on the bottom and velocity on the vertical axis. And so you see, this is a time 0, time 1 gigayear, time 10 gigayears. This is basically the lifetime of a galaxy. And you see that in the test particle simulation, what happens is that particles, as you well know, get trapped inside some resonance, right? We're dealing with a particular resonance here. That's what Lynden-Bell and Kalnice told us to do. And dark matter particles are getting trapped inside this resonance, and they're starting to perform this little make this little spirally structure because they're bouncing, basically. They're getting trapped and they're bouncing within the resonance. Now, as you know, linear theory doesn't recover this result. Linear theory says nothing about particle trapping. And so this is the result that Landau or Lynden-Bell and Kalnice would have given us. And it doesn't look anything like the final answer. So I must account for this particle trapping somehow. Of course, this is nothing more than nonlinear Landau damping. This is what O'Neill and Masitov did, I think, on opposite sides of the Iron Curtain in 1965. How do we do this in a galactic system? Well, what would you do in a plasma? You would move into the frame of the wave and you would look at oscillations of particles in the trough of the wave. That's exactly what we do here. The technical way to say that is we move into a new, we perform a canonical transformation into a new set of variables, one of which is a slow angle and one of which is a slow action. All this is saying is that we start to rotate with the bar, basically. Now, when you move into the frame of the wave and you average out stuff that you don't care about, you know what happens. You get a Hamiltonian that looks like the Hamiltonian of a pendulum. So this, in a plasma case, this would be the velocity relative to the trough of the wave, relative to the phase speed. And this would be the angle at which you're sloshing back and forth. And the effective Hamiltonian governing that motion is just that of a pendulum. And this is exactly what I was talking about at the start. These particles that are trapped at the bottom of waves are going to evolve back and forth like they're in a pendulum. What does this look like in a gravitational system? Well, now in the rotating reference frame of the bar, a dark matter particle, which was previously just doing its merry thing and going around and round, it now starts to get trapped like this. It's starting to get trapped on one side of the bar. So it only ever sees one side of the bar. This is called a horseshoe orbit. So we can do a nonlinear theory of this. We just need to use the pendulum equation. And you do a nonlinear theory, and rather than the linear theory result that you get in the center, you see what happens in time. So this is just evolved using the pendulum equation. This is not a simulation. You see that we get something really rather similar to what we have on the bottom left there. The particles are becoming trapped inside the resonance, and we recover the result that O'Neill would have expected. All right. I just gave you a spoiler for the next part. Time for audience participation. So Landau does linear theory, and he finds that the wave damps or grows, doesn't really matter, at some rate gamma. O'Neill or Masitov come along and say, well, you account for this trapping, and now I wait a long time, and what is the growth or damping rate that I get? Somebody shout. I heard somebody whisper. It was the right whisper. Huh? 0. Exactly. It's 0. So Tremaine and Weinberg in 1984 in the galactic case came along and showed that if you account for this trapping of particles, the final torque that you get is 0. Now, why is that? That's because the particles now, they started off symmetric. They've been sloshed around for a while, and then they get trapped in the resonances of the bar. But after a while, they start to look again symmetric. It's not the same symmetric distribution that I had at the start. It's a different symmetric distribution. But this is the almost in this case, fully phase mixed inside the resonance distribution. And so if I have the same number of particles on one side of the bar as I do on the other, I don't have this overdensity anywhere that's trying to pull the bar back. And so I get a torque of 0. Well, that solves some problems. Remember that Landau or Lynden-Bell Calomice were telling us that the bars should slow down because this torque was negative. Tremaine and Weinberg are saying, well, if you account for the nonlinearity, in fact, the torque is 0. There's the Lynden-Bell Calomice, there's the Tremaine-Weinberg result. So they're very, very different. Okay. So finally, for the last, how long do I have? 10 minutes. For the last 10 minutes of the talk, I want to tell you about what we did in this context, and then I'll finish off. So I was kind of worried about both of these theories, right? They're classic papers. They're extremely good papers. I strongly recommend that you read them. But there's a shortcoming. The shortcoming is that the dark matter particles in those theories, all they react to is the smooth analytic potential of the bar, right? It's an ultra idealized system. Whereas, of course, in real galaxies are not smooth at all. They have a lot of detritus, substructure, molecular clouds, whatever it might be, flying around. And so each individual dark matter particle is not moving on some beautiful rosette orbit. It's moving on that rosette orbit plus little jiggles. And so I was wondering what happens if you put in some jiggle on the right-hand side of this kinetic equation. Does all this beautiful, delicate resonant theory, does it just break down? So how does diffusion affect these delicate resonant phenomena? The way we do that is we use this equation here. So I replace the Vlasov equation, which would just be the left-hand side set equal to 0. I'm now using some dimensionless variables, don't matter what they are. I replace it with the simplest collision operator you can put on the right-hand side, which is just a diffusion operator. I could include a friction here, it wouldn't really matter. And also you can see Jeff's talk this afternoon for what happens if you put in friction. The diffusion coefficient here is what we call delta. Basically, delta being very, very small means there's no diffusion. Delta being much bigger than 1 means that diffusion really, really matters. So diffusion here means that each particle is not just going around its unperturbed orbit there, it's also jiggling up and down. So it's being kicked in its angular momentum, in its slow action variable, up and down. And so the question is, what happens? Now, why do people always use collision-less theory in galactic dynamics? They use it because of the thing that I told you at the start of the talk, the fact that the relaxation time was NT dynamical, which was much, much longer than the age of the universe. And so collisionless theory, well, it must be correct. The point, of course, is no, and this is well known in plasma physics. Kato and Tolman have been beating this drum for a while, that the diffusion time is the important time scale, not the relaxation time, but the diffusion time, the time it takes you to diffuse across the width of a resonance, which is a much, much easier thing to do. It's a much smaller fraction of phase space that you need to cover. And so this delta parameter can actually be in realistic situations, in realistic galaxies, and simulations of those galaxies where you have numerical diffusion can actually be quite large. So what happens, this also turns out is exactly the equation that was being used in tokamak theory to understand particle energization. So if you replace dark matter particles with ions and you replace the bar with an Alfvén wave, you have all of this beautiful theory that tells you how to solve this equation in the tokamak context. What happens is this. So these are the distribution functions for 4 different values of the diffusion strength delta. And I'll just show you, as I don't have that much time, what happens. So the first one is the one that you've already seen. This is the O'Neill picture. The particles start to get trapped inside the resonance and they start to swirl around there. In this top right-hand panel, I don't know if you can see it, but delta is 0.1 here. So diffusion is still only a 10% effect. It's only quite weak. But you see that now I have a blue wisp on the left-hand side and a yellow wisp on the right-hand side. And that's going to mean I no longer have this symmetry. The symmetry that told me that the torque ultimately was 0 has gone away. And so I now will get some torque. In this more unrealistic cases where delta equals 1 or delta equals 10, you might not have even known that there was a bar there in the first place. Much less happens in those cases because the diffusion is just dominating everything. The bar is unable to stir up the dark matter distribution. This is what the final distribution looks like. And so the question is, what does this do to the torque, right? That's the ultimate question. Does this really affect the Tremaine-Weinberg result? Well, we take the same formula that we had before. We needed to compute F. And now, rather than computing it from the Vlasov equation with 0 on the right-hand side, we computed with this from this equation with this delta on the right-hand side. What you find is this. So the blue line here, let's take this this dark blue line. This is the one where the diffusion is very, very weak. This is the Tremaine-Weinberg, or equivalently the O'Neill limit. And you see that the torque, this is the slowing rate of the bar, so basically the torque that the bar feels as a function of time. And so the bar initially feels a torque in one direction, then the other, and then it oscillates and it goes to 0. That's exactly what O'Neill told us should happen. But now if I take some large amount of diffusion, let's even say delta of 0.1, in the early stages, it looks very similar. And then it asymptotes to something that's not 0. So that's because I have introduced this asymmetry. And so I don't get a 0 torque, I get some finite torque on the bar that will slow the bar down, whereas the dark blue line would not have slowed the bar down. If I take delta to be very large, let's say the red line, then I just immediately asymptote to something that's basically up here, and it's 1. 1 corresponds to the Lynden-Bell-Kalnice torque. So Lynden-Bell-Kalnice, remember, they used linear theory. They didn't care about diffusion. And if you take nonlinear theory and you use diffusion, you recover their result in the limit of large diffusion. This is what this looks like. 4 minutes. This is what this looks like at late times. So this is the diffusion as a function of this diffusion coefficient. What is the torque on the bar that I get at late times? So Tremaine and Weinberg in the real universe is probably somewhere down here. If you think the real universe is described by cold dark matter, it's probably somewhere down here. Very, very small delta, very, very collision-less system. And so the torque that you get after a very long time is extremely small. But now as I increase this delta a little bit, it grows like delta to the 4/5. And eventually it peters out and it saturates somewhere close to 1, close to the Lynden-Bell-Kalnice value. If you think of some alternative model of dark matter, like fuzzy dark matter, or if you're just simulating dark matter on a computer, which means that you have artificial diffusion, you can very easily get deltas that are 0.1. And so you get some torque, which is significantly different from what you would have got in this collisionless regime. In other words, diffusion relinearizes the dynamics. So you start off with some nonlinear theory, you put in a lot of diffusion, and you get out the answer that you would have got had you ignored diffusion and ignored nonlinearity. I thought that was a pretty cool result. I thought that I'd actually discovered something. And then I realized, well, of course I hadn't, because it was all done 50 years earlier in plasma theory. Johnston and Auerbach looked at this in the 1970s. They were looking at the effect of Coulomb collisions on Landau damping, came to essentially exactly the same conclusion. So let me just finish by saying that we took a bit of plasma theory, we translated it into galactic dynamical language, and we were able to solve this problem that hadn't actually been addressed before in galactic dynamics of what happens to a resonance when you have some diffusion. But of course, that's a very, very generic question. And despite the fact that other stuff had been done on this in plasma literature, we ended up inadvertently giving you the most detailed study to date of what happens to a generic resonance in the presence of this diffusion. You know, I'm used to going to astrophysics conferences, so I haven't been to a plasma physics conference like this before, but I walk around these exhibition hall and I see that your exhibitions are for addressing the nuclear problem, fighting climate change, producing fusion, and so on. But you can now take these results and co-opt them and do whatever you want with them and put them back perhaps into plasma theory. And so maybe one day when you people have saved the world, our silly little study of bars inside galaxies will have contributed to that. So who said that astrophysics wasn't useful? Thank you very much.